Hello and welcome to the ACP Automation channel. In this video I would like to talk about the Siemens Simatic S5 110A PLC. The 110A PLC is one of the earliest PLCs to be introduced into the S5 family. I would say around about 1980ish, making this PLC almost 40 years old this year. Siemens classed this PLC as a modular type PLC as it is made up of individual modules, as can be seen here. The modules clip onto these connectors. The connectors in turn clip onto this ribbon cable. So I suppose on this PLC the ribbon cable is the S5 bus. The connectors and the ribbon cable in turn snap onto this 70mm DIN rail. The first module we will look at is this one here, which is the power supply. This power supply takes in a supply voltage of 220 volts AC. It then generates the required 5 volts DC to power the rest of the PLC. The presence of the 5 volt DC is indicated by this LED here. This switch here knocks the power on and off, so at the moment it's on. Turn it to here, power off, power back on again. There is also a 100 milliamp fuse located here. The next card we come to is this one here, which is the brains of the PLC, the CPU. The CPU has a slot here for an EEPROM memory submodule. However, the EEPROM modules which are used for this PLC have different part numbers to that of the newer PLCs. This module is a 6ES5 910 or AA31 and has a capacity to hold 2000 instructions. There was also a 1000 and a 4000 EEPROM available. The equivalent in bytes would be 2000, 4000 and 8000 bytes, as each instruction is made up of 2 bytes. As it states in the manual to only use this type of module, I would recommend only using the 6ES5 910 range of EEPROMs in this PLC. Interestingly, there wasn't any mention of a RAM module available for this PLC. I think this is because this PLC doesn't have any internal program memory. It just reads the program instructions directly from the EEPROM directly into its bit processor ready for execution. As the program is stored on an EEPROM, there are obviously no issues with losing programs due to flat batteries. On the subject of batteries, if we take this faceplate off, there's actually a battery underneath. So allow me to take the faceplate off and show you. So, with the faceplate off the CPU, we can see this strange square block here. This is a rechargeable backup battery. Why do we need a battery if the program is stored on EEPROM? Well, the PLC has the option of making some of its flags retentive. So if you have one of these PLCs and the battery has gone flat and the power goes off, the flag area will be set to 0 on power up and the PLC will stay in stop. We'll discuss this later on. Let me just clip the front back on. So, with the front cover back on, we can see there are 2 switches. Switch here, switch here. This switch here is the mode switch. In this position, the PLC is in run, and if I move the switch over here, the PLC goes into stop. You may note that when the PLC goes into stop, this LED illuminates here to show that the PLC is actually in the stop state. However, there isn't actually an LED to show that the PLC is running. This switch here is the retentive non-retentive switch. In this position, R, the flag area will be backed up by the battery, which we've seen before. So if the power goes off, on restart the flags will be in the same state as they were before the power went off. Interestingly, with the switch in this position, the battery is monitored by the watchdog. So if the battery voltage falls below 2.5 volts, the fault memory bit is set and the CPU will go into stop. So if this happens and the retentive function is still required, a new battery will need to be fitted, or the existing battery will need to be charged for about 1 minute. So after 1 minute, the battery will have enough charge in it to allow the watchdog fault memory to be reset. But it will take 3 days before the battery is fully charged. When the switch is in the NR, which is the non-retentive position, the watchdog timer is deactivated. The CPU also allowed inter-up processing to take place. However, the special input module was needed for this function to work. The CPU also has cycle time monitoring, This worked by a watchdog timer being set at the start of the program. When a block end or a block end conditional is processed, this made the timer reset back to 0. If a block end or a block end conditional is not processed within 300 milliseconds due to a programming error, say, the timer times out and puts the CPU into stop. One thing you may have picked up on is there is no actual programming port anywhere on the CPU. The early S5 PLCs like this one and the 010 didn't have the facility to plug a programmer directly into the CPU. So if you wanted to program offline, you'd have had to take the EEPROM out of the CPU and then plug it into a programmer like this, so it would plug into here, enter the program into the programmer, then blow the EEPROM, unplug the EEPROM, and then plug it back in to the CPU. The other alternative is you could actually buy one of these, which is a programming port. The programming port had a length of cable which comes out here with this on the other end of it. So you would unplug the EEPROM, plug this in where the EEPROM went, and then a cable from the programmer to the programming port. With one of these, you could write and modify your program online, and you could also monitor the state of the RLO and signal state like you can nowadays. I may do another video on how to actually use the programmer. The next card we come to is this one here, which is a 24 volt DC 8-channel digital input card. The status of the inputs can physically be seen on these LEDs here. This card here that's clicking away is a 24 volt DC 8-channel relay card. The status of the outputs are indicated by these LEDs on the front. As can be seen, they're quite happily flickering away there running the program. The final card that we'll come to is this one here, which is a 4-channel timer card. Another interesting thing with these early S5 PLCs like this one and the 010 is there wasn't a timer or a counter instruction in the PLC S5 instruction set. If you wanted to generate a time delay, you'd have had to insert one of these into the rack. The timer acts like an off-delay timer and is addressed with normal input and output instructions. So in this case, as the card is in slot 3, to start the timer you would set output 3.0, and to test if it is completed you would read input 3.0. You set the time base on the front using these switches here. These give you a time base of 0.01, 0.1, 1 second and tens of seconds. The fine tuning is then done by turning these pots on the side. There is also a test facility, so you can measure the time which you have entered is correct. I'll demonstrate how to test the timers now. First, put the PLC into the stop mode by switching the CPU into stop. Next, put the test switch into the test position. When I switch the card into test, you will see the timer outputs switch on for the duration set on the switches and pots. The outputs will be indicated by these LEDs here, as so. In this case, timer 3 is set at a time base of 0.01 and the pot is roughly at 5, which will give us a 50 millisecond pulse. I'll put the time base onto 0.1, so now we should get a half a second pulse. And as can be seen there, we did. Now I'll put the time base onto seconds, so this should now give us a 5-second pulse. Excellent. Right, well that comes to the end of my video. Hope you've enjoyed it, and please remember to subscribe. Thanks for watching. Bye.